Bismillahir Rahmanir Rahim. Assalamu alaikum and welcome to this session in which we are going to talk about analysis of queuing networks. We are going to focus on analyzing the performance of computer systems when we represent them as queuing networks. And we are going to mainly use techniques from the field of operational analysis, the field that we started talking about in an earlier session. And this field is specifically created by computer scientists and therefore is more applicable to the performance evaluation of computer systems and computer networks. We're going to study techniques both for open queuing networks and also for closed queuing networks. And we are also going to study techniques in which we do not do an exact analysis, but we give performance bounds. We will say that for this system, this is the best possible performance that you can have for a system of this specification. We will call this an optimistic bound. We can also talk of a pessimistic bound in which we would say that for this specification of a queuing network, this is the worst possible performance that we can get from a real system. And therefore, the performance of any system would be in between these two bounds. And therefore, this kind of analysis is very useful, and it is especially useful because it is very simple. We will start by talking about the analysis of open queuing networks. So in an open queuing network, you have requests coming in from outside the system, and they come into the system and they go to various devices that are inside the system, and after taking service, they go out of the system. So this is the definition of open queuing network. So let me make a distinction right here about queuing systems and queuing networks. Since we are mainly focusing on analyzing computer systems, we are representing computer systems as queuing networks because computer systems have many resources, multiple devices that can be represented as a queuing network, a network of queues. Therefore, I would use both these terms interchangeably. I would say a queuing system or a queuing network, but mainly we are referring to the modeling of a computer system by a queuing network. So to analyze such a network, let me first of all make clear the assumptions I'm making. So if you recall, we had studied earlier that in a queuing network, you can have different kinds of service centers. You can have a queuing service center, and you can have a delay service center. In a queuing service center, it is possible that the customer or the job which comes in would have to queue for service. But in a delay center, it's not possible because we are assuming infinite servers. So for the analysis that we are going to present for open queuing networks, we are assuming fixed capacity service centers and delay centers. So you can see the definition on the slide now. You see that for a fixed capacity service center, the service time does not depend on the number of jobs in the device. So in a sense, having more jobs in the queue does not increase the rate of the server as would happen in a multi-server queue. So an example of a fixed capacity service center is the CPU of a computer system. For a delay center, we are assuming that irrespective of the load applied, we do not have any queuing. Every customer comes in and gets service, and that service is usually defined by what is known as a think time. An example of a delay center would be a group of terminals in a computer system. And because the group of terminals are usually connected or are associated with humans, we do not represent that as a queuing center, but as a delay center with some known mean thinking time. So we're going to focus on just these two kinds of service centers, the fixed capacity service center and the delay center. And we are also going to make an assumption about exponential service distribution. We need this assumption to analyze an open queuing network. We simply cannot work only with operational assumptions. So while the other things that we'd be using, the other techniques would be still from the field of operational analysis, this assumption is not an operational assumption. we cannot verify in a real system in finite time that the service distribution is exponential. So we are making this assumption, and the rest of techniques we are using are from the field of operational analysis. So to understand how we can analyze open queuing networks, we first of all need to understand a very basic concept, the concept of a time average. So earlier we had talked about stochastic processes, and more specifically about ergodic stochastic processes. Ergodic stochastic processes are very nice in the sense that they have very predictable statistical properties. If you analyze just one realization of an ergodic stochastic process, we can know everything about that stochastic process. In other words, if we observe that process over a very long period of time to determine its time average, we also are able to determine its ensemble average, because the various different realizations of an ergodic stochastic process have a sameness about them. So we can say that the time average of a realization of an ergodic stochastic process is equal to the ensemble average of that stochastic process. In other words, still, the time average is equal to the steady state stationary averages of that system. So that is very useful, but still for a time average we need to observe the system at all times. So if you recall our discussion on the fundamentals of queuing theory, in which we talked of Poisson processes and the pasta principle, we highlighted that a time average is like a continuous average. You look at the instantaneous queue lengths at all times, you integrate over all time, and then you divide over total time to determine the time average. This can be difficult, but for a Poisson process this is very easy because of the pasta property. We'll come to it very shortly, but the general idea is that when a customer comes into the system, it observes the system in some state. Now our question is that if we only observe the state of the system at arrival instances, do we get exactly the time average? Because a time average would require infinite number of observations or complete information about the system. But for a customer average, we're only observing the system at discrete points in time. So the question can be put that can the time average be calculated at arrival instances always? The answer to this question is that not generally, but for some particular processes and systems we can, and that is a very useful property. But let me first of all show you a place where this does not apply. Consider a DD1 system with inter-arrival times of 1 and service times of 0.5. So every time, because this is a deterministic system, the arrival would come and it would be serviced in 0.5 units, but then it would wait for another 0.5 units before the next arrival comes. So in general, you would see that the system is busy only half of the time, and it is busy with only a single customer. So we can see the graph on the screen, and that illustrates this property that the system is only busy half of the time, and half of the time it has one customer, and the remaining half it has 0 customers. But if we only observe the arrival instances, we see that whenever an arrival arrives, it sees that the system is idle. So in this sense, the arrival average and the time average are not identical. So this arrival average and time average, both of them are not identical all of the time, but for a Poisson process, they are in fact identical. Let's have a look at this on the slide now. We see the instantaneous queue lengths, and we can also see the queue lengths just before the arrival. So you can see that before the first arrival, we did not have any customer in the system. For the second arrival, before that arrival came, we had one customer in the system. And therefore, at every arrival, we can sample the state of the network, and that can be seen on the screen now. Therefore, arrival averages can be calculated as a simple arithmetic average, unlike the time average, which requires us to integrate over all time and then distribute that area over all time. So in that sense, arrival average is very useful, and the important property here is that arrival average is identical to the time average if we consider that the arrivals are Poisson. So that is a very useful property about Poisson arrivals. In other words, the distribution of customers seen in the system by the arriving customer is the same as would be observed by some random observer which is observing over all times. So that is the arrival theorem as it relates to Poisson processes, and this principle is known as the Pasta principle. Poisson arrivals, see time averages. Can we extend this principle to open product form queuing networks? If you recall, we had earlier discussed product form queuing networks or also separable queuing networks, and we said that these are the queuing networks that we can efficiently analyze. And if the product form queuing network is an open network, then the arrivals are coming from outside the network, taking service and then going out. But can we have this principle of the relation of arrival averages and time averages in such a network? So in fact, luckily we have such a relationship, even though it's not necessary that the arrivals are Poisson. So we have a counterpart principle known as the Asta principle, or the arrivals see time averages, and this applies if we have a product form queuing network. So it's important to realize that this applies only to open queuing networks that have a product form distribution of the solution. So in an open product form queuing network, the arrival average is equal to the time average of the same network. So the reason I highlight the same network is because when we consider closed queuing networks, the arrival averages are equal to the time average of the same network but with one customer less. And that would be a distinction that would be important for analyzing closed queuing networks. But for now, we see that this is a direct analogy with the principle that we studied for Poisson processes. Asta is just like Pasta when we are considering open product form queuing networks. So using this principle, we can determine the response time faced by a customer that arrives at a queue in an open product form queuing network. So you can see on your slide that we have a relationship Ri is equal to Si into 1 plus Qi. The reason we have this relationship is because on average, whenever a customer arrives at a queue, it expects to see the time average of the same network already there, of the same queue already there. And we've just seen that this time average for Qi is equal to the variable Qi. So we expect Qi number of customers already there at the ith queue, and now the customer is also coming in. So all in all, we have 1 plus Qi customers that have to wait for service. And therefore, the mean waiting time, which is Ri here, is equal to Si, the service time of the ith queue, multiplied by 1 plus Qi, which is the number of customers there are. This equation is a very important equation, and we would call this the Asta principle for open product form queuing networks. To analyze open product form queuing networks, we require another relationship, and that is a relationship that we've already covered in much depth, that is the celebrated Little's law. So we see that we can apply Little's law to a queue that is part of a queuing network. If we are considering the ith queue, we have the relationship that Qi is equal to Xi Ri. So earlier we've seen the relationship of Ri with Si. We saw that Ri is equal to Si into 1 plus Qi. And we also now have another relationship involving Ri, and that is equal to Ri is equal to Qi over Xi. And this is the arrangement of Little's law. And making use of this, we can now solve for any device center in an open product form queuing network. Importantly, in a product form queuing network, we can analyze every device independently. And that is one of the reasons we are able to analyze product form queuing networks. So as mentioned right at the start of this lecture, we talked of that, this analysis only is applicable to fixed capacity service centers and also to delay centers. So let us now analyze after giving all these results. We are going to make use of these and find out results for a single service center in an open product form queuing network. So first of all, let's see how we can determine the mean queue length. So we will initially talk about the queue length for fixed capacity center. From Little's law, we have that Qi is equal to Ri Xi. But we also have a relationship of Ri from the Asta principle, and that was that Ri is equal to Si into 1 plus Qi. So making the change in the first equation, we get the second equation shown on the slide. And from that, we can make use of utilization law to express Xi as Ui over Si. We're trying to get a result which is analogous to stochastic analysis of service centers. And we would see that the result that we have is the same as the result we had earlier when we were considering MM1 queues. So up till now we have Qi is equal to Si into 1 plus Qi multiplied by Ui divided by Si. If we arrange this and solve this algebraically, we get the equation Qi into 1 minus Ui is equal to Ui, and after some more rearrangement, we get the final form that Qi is equal to Ui over 1 minus Ui. And this is the operational analysis result for fixed capacity center. And let me now show you the result that we had for stochastic analysis of MM1 queue. There we were talking about expected number of customers in a queue, and the formula we had then was rho over 1 minus rho, where rho was the stochastic version of utilization. So we see that we have identical results, and this actually highlights the usefulness of operational analysis. We've made less assumptions. We have not made any assumptions about stationarity of the stochastic process. We have not made any assumption about the ergodicity of the stochastic process. We have made only very few assumptions. One assumption that we have made is the exponential service time distributions of the various device centers. And from that, we have the operational analog of the result that we had for stochastic analysis. Let's now calculate the queue length for a delay center. And this is relatively easy. We note that from Little's law, we have the relationship that Qi is equal to Ri Xi. But for a delay center, the mean waiting time is just the service time. There is no queuing there. And therefore, Ri is just equal to Si. So when we replace Ri by Si, we get Qi is equal to Si Xi. But if you remember, we had an operational law which expressed Xi Si as equal to Ui, or the utilization of the ith device. And therefore, making use of the utilization law, we can now express Qi as equal to Ui. So we know that from this relationship that the mean queue length of the ith device is just the utilization of that device, and the stochastic analog of this is also identical. We just have, instead of the operational variables, the stochastic variables. The expected value of n for an MM infinity queue, which is the infinity server queue, which is the delay center, that thing is just equal to rho, and rho we know is equal to Ui. Okay, we can also calculate response time. These are the two important parameters that we'll be focusing on, the queue length and the response time. So for a fixed capacity center, the device response time can be calculated as Ri is equal to Si into 1 plus Qi, which is just the ASTA principle, the arrival C time averages principle of open product form queuing networks. We've just discovered that Qi is equal to Ui over 1 minus Ui, and in the first equation we had the term 1 plus Qi. So if we put Qi there, we get the formula that Ri is equal to Si over 1 minus Ui. This is again identical to the relationship we had for stochastic analysis of MM1Q. The reason I'm showing both these things together is to highlight the commonality and also to focus on the similarities between the two approaches. These two approaches are complementary approaches, and operational analysis is more intuitive and also the assumptions are weaker. So let us now try to analyze this equation intuitively. So we've seen the equation, but what does it mean? It basically means that the mean response time of the ith queuing device is just the scaled version of the service time of that device. And that scaling factor is how busy that device is. If the device is very busy, your response time would increase more. And that is precisely the intuition that we developed from the stochastic analysis from MM1Q, where we saw that the expected response time is equal to the service time 1 over mu divided by 1 minus rho. So this was the device response time for a fixed capacity center. We can now talk of the device response time for a delay center. And this is precisely what we used in the calculation of the mean queuing time. We said there that in a delay center, there is no queuing. So the response time is just going to be the service time. Regardless of how many customers come into a delay center, if you have a delay center, we are assuming infinite servers. And therefore, the value of Ri would be just equal to Si. And this is essentially the same formula that we had for MM infinity Q, where we had the response time as equal to 1 over mu. So we have again an analog, an identical result. The difference is just that now we are using operational variables. So this completes our discussion on the operational analysis of service centers in an open product form queuing network. So while we use stochastic analysis for the discussion about service facilities, while they were not networked, for queuing networks, we're going to focus on operational analysis. The reason being that this analysis is more relevant to the modeling of computer systems, and also because it uses weaker assumptions. After the discussion on open product form queuing networks, now we can start our discussion about closed product form queuing networks. And for this, we are going to study the mean value analysis technique. Let's solve the closed queuing network and give performance measures without calculating many of the underlying distributions. So for MVA, we do not calculate the marginal distributions, the joint distribution, or the normalization constant. If you recall our discussion on Gordon-Newell networks and closed-Jackson networks, we saw that in such networks, we have to calculate a normalization constant. And we also said that earlier we had a framework for calculating this, which is known as convolution algorithm, proposed by Jeff Busen, but it was computationally intensive, and it also had some numerical instability problems. In mean value analysis that we are going to focus on, we actually ignore the need of calculating the normalization constant. We make use of a modified version of arrival theorem, which is modified to address the intricacies of a closed queuing network. In a closed queuing network, we have kind of a negative feedback, in which if a customer is arriving at a particular queue, it cannot be in the network anywhere else. And because the number of jobs in the system are fixed, so we have this now kind of dependence in the network. And accordingly, even the arrival theorem is modified. Let's start this discussion by first of all identifying the Little's law that is relevant to our discussion here. Because we are considering a closed queuing network, we will be considering the central server model, in which we have a CPU, we have some other devices, and we also have some terminals. And therefore, we can make use of interactive response time law. So that, as we studied earlier, is just a specific form of Little's law. You can see that on the slide. We see that Ri of n is equal to Qi of n divided by Xi of n minus z. So let me just tell you what this notation means. Ri of n means the response time that we'll be getting from a queuing network that has n jobs. If we had n minus 1 jobs, we would have written Ri n minus 1. Similarly, when we say Qi of n minus 1, this is telling us the queue length in the ith queue when we have n minus 1 jobs in the entire queuing network. So this is the first law that we'll be using for our analysis, the mean value analysis of closed queuing networks. The second important principle is a modification of arrival theorem as it relates to closed product form queuing networks. So for this, I would tell you what this principle is. It basically says that in a closed product form queuing network, arrivals to a Qi see the queue at equilibrium with Qi n minus 1 customers, where Qi n minus 1 is the steady state time average queue length for device I for the same queuing network which originally had n customers but now with 1 customer less. In other words, the arrival average is equal to the time average of the original network having 1 customer removed. So the arrival theorem for open queuing networks was that the arrival average is equal to the time average of the same network. But for a closed queuing network, the arrival average is equal to the time average for the same queuing network but with 1 customer removed. And because of that, we can calculate the response time at any Qi using this formula, that Ri of n is equal to Si multiplied by 1 plus Qi of n minus 1. Because when a customer arrives at a queue, it will see Qi n minus 1 customers already there. So it would have to wait for service for them, and then it would take service itself. And from this we can calculate Ri of n. So the important thing here is that now we have 2 versions of Ri of n. In other words, the mean waiting time depends on Qi n minus 1, which is the same network but with 1 customer less. And from Little's law, it had a dependence on Qi of n. So there the dependence was on the mean queue length for the same network. But now we are considering in arrival theorem the dependence between Ri of n and Qi n minus 1. So this is an important principle, and it relates the mean service time, the mean waiting time, to the queue length for the same network and to the queue length of the same network with 1 customer less. Because of this, we can make use of iteration to calculate the performance measures for any value of n. We can start from n is equal to 0. From that we can calculate the performance measures for n is equal to 1. And from there we can calculate the performance measures of n is equal to 2, and so on for any value of n. So here we are calculating mean values. If you note here, we are not having any distribution here. We just have Qi of n, which is the mean queue length. We do not know the probabilities of different values of customers being in the queue, and that is one limitation of MVA. Using MVA, we cannot determine the joint distribution of some distribution of jobs across the queuing network. So if you have a queuing network, let's say having three devices, we cannot determine what is the probability that you would have 30% of the customers there, 40% of the customers here, and 30% of the customers here. The probability distribution cannot be calculated, but what we can calculate is the mean performance measure, and that is important in many cases. In having information about distribution is important, but we do not need it in all cases. And in cases where we do not need information about the distribution, information about mean values is very important. We get information about these mean values by Little's law and the arrival theorem for closed networks that we just studied. So using this, we've seen that how Ri depends on Qi of n, and it depends on Qi of n minus 1. We can now determine all the performance measures, the mean values of them. So for example, we can calculate the system response time, and that is calculated using the general response time law. So we would have the value of Rn as equal to the summation over all devices, the visit counts to individual devices, and the device waiting times. So this will give us the system response time. We can also determine the system throughput, and that is calculated by the rearrangement of the interactive response time law. From the rearrangement, we see that x of n is equal to n over r of n plus z. So we know r of n, z and n are already given to us. From this, we can calculate the system throughput. We can also determine from these the device level throughputs. That would be calculated using the forced flow law as shown on the slide. We can also determine the device queue lengths. So Qi of n would be calculated as Xi of n into Ri of n. We've determined Ri of n, we've determined Xi of n. From that, we can calculate the device queue length with n jobs in the network. This is just the application of Little's law. We note here that for delay center, the mean waiting time is just the service time. And the relationships that we've shown for the device throughput and the device queue length also apply to delay center. So let us now study MVA through an example to illustrate its salient points. So in this example, we have a central server model in which we also have terminals. We have a CPU and we have two disks. So we call the first disk disk A and the second disk is disk B. So this is a time sharing system. Each user request makes 10 IO requests to disk A. From this we know that VA is equal to 10. The visit counts to device A is equal to 10. And we also have 5 IO requests to B. So VB then is equal to 5. The service time per visit is given for both disk A and disk B, from which we have SA is equal to 0.3 and SB is equal to 0.2. We note here that this is the service time per visit. We can also talk about service time per request, because every request can make multiple visits. So there is a distinction here. So in the question itself, we are given that each request takes 2 seconds of the CPU time. So D CPU then is equal to 2. This is not the service time, but this is the service demand, because we are considering all the visits to the CPU here for a request. The user think time is given to be 4 seconds, so Z is equal to 4, and we are given that we have 20 terminals. So from the information that we have, we can determine some further important variables. So for device A, in the question itself, we are given VA and SA. So we can calculate the service demand of device A, which is equal to 3. So DA is equal to 3 here. We also are given VB and SB. From that we can calculate DB, which is equal to 1. We are given VA is equal to 10 and we are given that VB is equal to 5. Since this is a central server model, the visits to the CPU would be equal to the visits to individual devices plus a visit that the external request makes when it first comes. And therefore, vCPU is equal to 16. We are given dCPU and we are given vCPU. From that we can calculate sCPU, which is determined to be 1 over 8. Now we can show how MVA works. We start by initializing the system. So when I say we are initializing the system, we are talking of the performance measures when there is no customer in the system. Obviously, in that case, when there is no customer in the system, the steady state queue lengths are going to be 0 because there is no customer in the system. We can bootstrap from here. We can start from these values and we can then consider what will happen when we have one number of user in the system or we have one number of job in the system. N is equal to 1. So when that is the case, we can determine the device response time using the ASTA property. So we can determine RSCPU as being equal to sCPU into 1 plus QCPU. So this is just the ASTA principle, and we make note here that the QCPU that we are using here is the queue length when you have one customer less, which is what we had in the initialization phase. We determined then that QCPI is equal to 0, QA is equal to 0, QB is equal to 0. We are going to make use of these here. So the response time, the mean response time of CPU then is calculated using ASTA property to be 0.125. We also determine the mean response time for RA and RB. So these are only the device response times. From this, we can calculate the response time of the entire system. The entire system is composed of all these devices, and all these devices are visited according to a known visit count. And therefore, the system response time can be determined using the general response time law. That is shown on the slide. R is calculated as the product of RCPU, vCPU, plus the product of RAVA, plus the product of RB, VB, and this thing is calculated to be 6. The system throughput can now be calculated by the application of Little's law. Little's law can be expressed as X is equal to N divided by R plus Z in the case of an interactive terminal queuing network. And this system throughput is calculated to be 0.1. So this is the number of completions per unit time of the entire system. But what is the throughput of individual devices? We can also determine those using forced flow law. We can also determine the device queue lengths for N is equal to 1. And we make use of forced flow law and Little's law. And we combine them to determine the value of the mean queue length for N is equal to 1. And this completes our first iteration. We can make use of the values that we calculated at the end of this, the device queue length, to bootstrap the next iteration. For the next iteration, we'll be making use of the device queue lengths for N is equal to 1. And from that, we'll be calculating the performance measures of N is equal to 2. Let's have a look for iteration 2. We determined that QCPI was 0.2, QA is 0.3, QB is 0.1. And from that, in the second iteration, we can calculate the device response times using the ASTA property. We can determine the system response time using the general response time law. We can determine the system throughput using Little's law as applied to an interactive terminal-based queuing network. And from that, we can calculate the device queue length when N is equal to 2. And that can be used to calculate the performance measures for N is equal to 3. So it becomes obvious then that this is an iterative algorithm. If you want to calculate the performance for some high value of N, you have to start by iterating at 0 and successively iterate further to get to the desired number of N. In the current era where we have ample computational tools available, this is not much of a problem. But we also have some approximation algorithms for doing MVA. We are not going to get into those today, but you can have a look at those from the textbook. So on the slide now, you can see first of all the fact that to determine the performance measure for n is equal to 1, we need to determine the performance measure for n is equal to 0. And similarly, we have to do the same iteratively for higher values of n. So we see that in a tabular form, the various values that are associated with various iterations for the device response time, the system response time, the system throughput, and the device queue lengths. This then concludes the example on MVA. Let me wrap up this discussion on closed queuing networks and their analysis by MVA by highlighting the drawbacks of MVA and where we are making assumptions. So the first thing is that MVA is only applicable if you have a product form queuing network. The second thing is that we are making some assumptions here. And while we will not be able to cover all those assumptions in depth, I will encourage you to read the textbook to see what are the assumptions that we are making. The two assumptions that I will talk about are the one-step behavior property and also device homogeneity. So the one-step behavior property is that we do not have multiple jobs transiting at the same time from different queues to different queues. So one thing happens at a time. And you also have device homogeneity, which basically means that the service time of a device does not depend on the queue length and also where the different customers are in the queuing network. So for this, we are also making the assumption that either we have fixed capacity centers or we have delay centers. And we are also making the assumption of exponentially distributed service times. This completes our discussion on closed product form queuing networks. I'm going to talk about another technique now for analyzing queuing networks. And this is not going to focus on exact analysis in the sense that we get exactly the performance for the network, but here we'd be considering the bounds of performance. Using some very simple methods, we can talk about optimistic bounds and pessimistic bounds. Optimistic bound refers to the bounds on performance which we cannot exceed and get better performance. So in this sense, it is defining the best case scenario. This is the best performance that you can get from the system. We also have pessimistic bounds, which basically defines on what is the worst performance that you can have from the system. Using these two bounds, we can then know something about the system, that the performance of the system would be in between these two bounds somewhere. This analysis is important because for this we are not making a lot of assumptions, and this is very understandable to managers because we are not making any of the standard stochastic assumptions. We are making a singular assumption, and that assumption is that the service time does not depend on the queue length and where the various customers are in the network. So with this assumption, we are able to get very general results, and those are very useful for determining the primary factors that are affecting performance. We're going to focus on asymptotic bounds. First of all, we're going to consider one extreme in which there is no queuing, or we have very lightly loaded conditions. This will allow us to calculate the optimistic bounds. And then we will consider the other extreme of very heavy loads, and that will allow us to calculate the pessimistic bounds. There is another kind of technique which is known as balanced bound technique of determining bounds, in which we distribute the entire load of the system equitably across all the devices. In other words, the utilization of all the devices are made balanced, or they are made equal, but we're not going to focus on that in this session. We're going to focus only on asymptotic analysis. This is a very general technique and applies more broadly than the technique of balanced bounds. But the offsetting factor is that balanced bounds actually provide tighter bounds. So they provide more information. So our focus is on asymptotic bounds. We can see graph on the screen now. You see the relation between MVA and asymptotic bounds. In this case, we are showing the optimistic bound. So MVA gives us the exact performance measure for throughput and response time as a function of n, the number of users. But if we only consider the asymptotic bound, it is going to tell us the primary bounding factors, and it will tell us what is the best possible performance that we can have from the system. And that is shown on the slide, and this then informs us about what is the best possible performance and also what are the factors that are holding us to this performance. I'll just like to briefly recap the various classes of workload types. We have essentially three types. The first type is transaction workload, which is used in an open queuing network. It is specified by the arrival rate. And in an operational network, the arrival rate is equal to the throughput. But the important thing is here that the arrival rate can vary. It's not fixed, and also the jobs are coming from outside the queuing network and depart after getting service. The other two workload types, the batch workload and terminal workload, refer to closed queuing networks. Terminal workload is relevant to a queuing network in which you also have terminals and you have fixed number of jobs. So if we have a terminal workload, we need to define or characterize it by specifying the number of jobs and the think time of the terminals. If we have a batch workload, we need to specify it using the number of jobs in the system. Okay, let us now start by talking about transaction workloads. In transaction workloads, we can determine the optimistic bound. So whenever you have a queuing network, there are multiple devices, but there is going to be, in general, at least one device which reaches 100% utilization before all the other devices. And at that point, it is saturated in the sense that it cannot accept any more requests or cannot process them. And therefore, the entire throughput of the system then becomes dependent on this bottleneck device. It turns out that if we know the service demands of all the devices in the network, the device that has the highest service demand is the bottleneck device. And that actually limits the maximum performance that we can have from the system. So if we have multiple devices and they have their own service demands, D1, D2, D3 and so on, the device that has the maximum service demand is specified by the notation Dmax. The device that has Dmax is the bottleneck device, and the maximum throughput that we can have from this transaction workload queuing network is equal to 1 over Dmax. For the response time, the lower bound is when we have no queuing at any of the devices, and then for that the response time would be just the sum of the service demand over all devices. We represent this by the variable d, and this is the summation over all I of di. Unfortunately, we cannot specify an upper bound on the response time, and this is because irrespective of what the arrival rate is, consider the arrival rate as lambda, we can consider bulk arrivals in which n customers are coming after n over lambda time units. So the arrival still is lambda, but because now n customers are coming together, most of the customers would have to wait for a long time. And you can make this n arbitrarily large, and therefore we determine that there is no maximum response time. There is no upper bound on the response time, and there is no lower bound on the throughput. Fortunately, we have more insightful results for batch and terminal workloads. In those cases, we have fixed number of jobs in the system, and therefore we can determine both the optimistic bound and the pessimistic bound. We're going to focus on the case of terminal workload, and the results for batch workload can be determined from that by just assuming the average think time as equal to 0, because there are no terminals in a batch workload. So in the case of terminal workload, first of all, let's see the bounds on throughput. The pessimistic bound on throughput is when you have maximum queuing. And when do we have maximum queuing? When every customer that goes onto a queue will find all the other customers already present there at the queue. And therefore, it would have to wait for their service before it can get service of its own. And therefore, for a single customer, the throughput it can get is equal to 1 over nd plus z. And in general, for n number of customers, the throughput that it will get would be n over nd plus z. The case in which we have no queuing, that would define the optimistic bound. And for that, we have two bounds. The first bound relates to the bottleneck device. So your throughput has to be less than or equal to 1 over d max. And that is a constraint due to bottleneck device. There is another constraint due to low load. In that case, you do not simply have enough number of customers to get a high enough throughput. In that case, when we only have one customer in the system, the throughput that we have is 1 over d plus z, and in this case we are assuming no queuing. When you have n number of customers, you would have n over d plus z, and this is essentially the upper bound, because at this point we are going to intersect 1 over d max, and that point defines the knee point. This is the optimal point, and we actually strive to operate a network here, because increasing the number of jobs or the number of customers above this is not going to give us any additional performance benefits. In fact, performance is going to deteriorate. But if we have lesser number of customers in the system, we are not using the system enough. So these were the throughput bounds. We see that we have a pessimistic bound, that the throughput must be greater than n over nd plus z. And we also have an optimistic bound. We have two values, 1 over d max, and the other one is n over d plus z. Whatever is the minimum of this defines the optimistic bound. We can determine the response time bounds from this as well, and we determine the bounds on x of n. From that, we can determine the bounds of r of n using the interactive response time law. Our optimistic bound is determined on the assumption that there is no queuing, and our pessimistic bound is based on the assumption that there is maximum queuing. Let's have an example to illustrate this and highlight what we are talking about. So if we have a network, D CPU is given, DA, DB, and Z is given, we are asked to determine the QN's, this queuing network's best possible performance. So from the given data, we can calculate D as the sum of all the service demands, that is equal to 12. The maximum service demand or the bottleneck of the bottleneck device is equal to 5. And then we have these bounds through which we can determine the performance bounds. So we can see two lines shown on this graph in which we are comparing the readings that we had from MVA to the bound. The first line is a function of n, it is equal to n over 30, and the other line is a constant 1 over 5, and that bounds the performance. The performance cannot be any better than this. Similarly, for the response time, the optimistic bound is shown, and our performance cannot be better than this. Let me now conclude this session by talking over the most salient points of this session. In this session, we talked about MVA analysis, and we said that we can use it to analyze closed queuing networks. We can also analyze open product form queuing networks using techniques from operational analysis and the assumption that we have exponential service time. We also talked of performance bounds, and we stated that these provide insight into the primary factors that affect the performance of a queuing network. I will see you next time, inshallah. For today, it's Allah Hafiz from me. Assalamu alaikum.